All right, in 2.7, the last section of this chapter, measures of spread of the data. Okay, so by spread, we mean variation. Variation is the degree to which the data are spread out, okay, in really easy terms. Now, different ways we measure that. The one that you're familiar with is range. Okay, range is simply the max minus the min value. Okay, that's all you do is subtract. It's easy to do. But the thing is that the range is not resistant. Remember that word from our previous video. It is not resistant. If a distribution it has a tail on it, that range has to include that maximum value. So it's going to get pulled toward the tail. So the range is computed using only two values in the data set, the smallest and the largest. Now the other two measures of spread we're going to talk about, variance and standard deviation. They all use data in their computations. So none of these are actually resistant to these outlying points way out here. All right, so not resistant, catch that, it's not resistant. So we really don't use range very much. Now, the next measure of spread that you need to know is the standard deviation. It's a measure of the spread of data. Now, consider the standard deviations for the following two sets of data, both with the same mean of 100, okay? So notice this. Here's my set of data. They have a mean of 100, but the standard deviation is 0. What does that mean? It means that the difference between each point and the mean is just 0. They don't deviate from the mean much at all. So standard deviation is, think of it as deviate from the mean. How much does a set of data, each piece of data, deviate from the mean, really? Okay. Now look at this set of data, 90, 90, 100, 110, 110. So it still has an average of 100, but look, the standard deviation is 10. How much does each piece of data differ from the mean? Well, around 10, you know. This one has no deviation, but this has a deviation of 10, 10, 10, 10. So the standard deviation, how much do they typically differ from the mean? That's what's happening with standard deviation. Now, to calculate it, you need two formulas that you got to know, all right? Population standard deviation is right here. Now, notice the sigma symbol right here. This little guy is called sigma, okay? And it's really important that you know it. It's kind of sideways 6. It means population standard deviation. If it reflects the population, it's the parameter, right? It's a parameter. Now the other formula is the sample standard deviation, meaning it is a statistic, right? Because it came just from the sample. So I want you to notice what's going on in these formulas. It's the sum of each piece of data minus its mean, and you square it. So you add all those up, divide by the total, then take the square root. And I'm going to walk you through some of these problems. Now, notice the difference between this formula and this formula. The only thing that's changing here is n minus 1. That does make a difference in your answer. So it's really important that you catch. You got to read the question carefully to know, is it talking about a sample or is it talking about a population? Because your formula does change. When we did averages, the formula doesn't change, but when you do standard deviation, indeed it does. All right? So, by the way, for units for standard deviation, it takes the same unit as the data. Okay? So if it's puppy dogs, it has a standard deviation of 3 puppy dogs, whatever. Okay? Important properties you need to know. The standard deviation is a measure of how much the data deviate from the mean, like I said. The value of the standard deviation can never ever be negative. If it's 0, that means all the values are exactly the same. Okay, it's a measure of distance, how far from the mean. So distance can't be negative, so standard deviation will not be negative. Larger values of standard deviation indicate greater amounts of variation. That hopefully makes some sense. That data does not follow a pattern. Outliers, and we'll define outliers or we did define outliers before, can drastically change the value of your standard deviation, okay? It's going to change things up. Now, standard deviation is one measure of spread. Another one is variance. Variance is a deviation about the mean. All it really is the square of the standard deviation. That's the easiest thing to remember. It's just standard deviation squared. So now, to do population variance, okay, it's just the same standard deviation formula we had right up here. We just took the square root off. Notice the symbol is sigma squared. It's important that you know sigma is the population. Now, sample variation is the sum of the squared deviations about the sample and divided by n minus 1. Again, it's just everything under the radical up here, it's just you didn't take the square root of it, okay? So now how are we going to calculate these? Here's the steps you're going to take, and we're going to walk you through this, okay? We're going to calculate x bar, the sample mean, or mu, the population mean. For each observation, we're going to calculate the difference between the data value and the mean, okay? That's what the x1 minus the x bar is, okay? Data value minus its mean. Then we're going to square each difference. Then we're going to sum the squared differences, okay, or add, if you'd rather say add the squared differences that are calculated. And divide the sum by n minus 1 if it's a sample, but divide by n if it's a population. This really does matter. This is where it changes. This is where it's important. The answer for this step is what's called the variance, okay? You stop right here if it's asking you for variance. Step 6, we're going to take the square root of the variance that we took of step 5. This is called the standard deviation. Okay? So, let's do this. Compute the data, represent the first scores. Scores on the first exam of 10 students enrolled in the Intro to Stats. Here it is. Now, on a previous lesson, we found the mean of this was 79. Okay, so I'm going to save us that. Okay, we added them up, divided by our 10, and go from there. Now, it says first exam of 10 students enrolled. So we're going to assume that n is a population, so n is 10. All right? Now, compute the range. Remember, the range is the max minus the min. So let's find the maximum score was, what, 94? And the minimum score was 62. So I subtract and I get a 32. All right? Now to compute the variance, I need to do some things, okay? I'm going to do first, we're going to take each score and subtract the mean. Okay, we're going to subtract 79. So 82 minus 79 gives me 3. Negative 2 gives me 11. And it's okay if it comes out negative, that's not a problem. And then 68 minus 79. That's positive 5. 94 minus 79. All right, so I found my differences. Now the next thing I need to do is to square the differences. So I take those differences I just found and I'm going to square them. That's all I'm doing. 3 squared is 9, negative 2 squared is 4, 121, 64. 17 squared is 289, 121, 25, 25, 225, and 81. All right? So there are my squared terms. Now the next thing I need to do is add, right? If I add these up, I get a total of 964. Now, for variance, variance says I take this total and I divide by n. Since this is a population, we're going to divide by 10. So my variance is 96.4. All right? Now, to move that to standard deviation, all I have to do is take the square root of my variance. Okay? So I'm going to take the square root of 96.4 and find out that my standard deviation is 9.818. Okay? That's all there is to it. I know it's a little technical. So there's my standard deviation, and there's my variance. All right? Just one more step to get standard deviation. So let's look at another example. The Insurance Institute of Highway Safety crashed the 2007 Audi A4 4 times at 5 miles per hour. The cost of repair for each of the 4 crashes were as follows. Compute the range, the sample variance, and the sample, keyword, sample standard deviation of the cost to repair. Okay, so easy enough. Let's do range first. Okay, range is max minus min. Well, there's max. 2038 minus the minimum is 918. So that gives me a range of $1,120. Easy. Now, remember sample variance is right before we get to sample standard deviation, so we can run through this really quick. So we're going to list out my x values. 976, 2038, 918, and 1899. Now, in order to do this, however, I need to find the x bar. Remember, the sum of all my x's divided by n? Well, if I add these 4 up, divide by 4, I get 1457.75. Okay, it's a gross number. I agree, but you have calculators that can help you. Now, if I take x and I subtract that x bar number, okay, I'm just taking 976 and I'm subtracting the 1457. I get a difference of -81 and 75. 2038 minus 1457 gives me a positive 580.25. 918 minus x bar gives me negative 39.75. Oh, yeah. And 1899 minus that gives me a positive 441.25. Okay, remember the next thing is to square those results. So if I square these numbers, they're going to be really big and gross, but you have a calculator to help. It's okay. So I get these numbers. Then I add them up, and I get this ginormous number. Okay, that's the sum right there. Now, to get variance of my sample, I'm going to take this number, and I'm subtracting by n minus 1. So if n is 4, I'm going to divide by 3. So I get a variance of 351,601.58. All right? That's the variance because it's the s squared. Now to get s, I'm taking the square root of that number. And I get 592.96. Since we're talking dollars, we'll just knock it down to 2 decimals. Okay? This is the variance. This is the standard deviation. Okay? Notice the only thing I had to do was take the square root a variance to get there. Okay? Now, comparing values from different data sets. You will have, by the way, you will have a lot of practice on this standard deviation calculation stuff because you do need to know how to do it by hand. It is time consuming, so I don't know that I would give you too many questions like this on a test, but I would give you simple numbers to do it with at least, okay? Now, comparing two different data sets, there's something called a Z-score. It's the number of standard deviations that a given x value is above or below the mean. A Z-score is unitless, okay? No unit on your answer, okay? It has a mean of 0 and a standard deviation of 1. Always, always, always. All right? So let's look at some formulas. Here's the formula. For a population Z-score, you take the mean, or take the observation piece of data you have, subtract the mean, then divide by sigma, the population standard deviation. If it's a sample, notice it just changed to x bar and s here because we're using these sample values. So let's just try this. It's not that hard, okay? Determine whether the New York Yankees or the Philadelphia Phillies had a relatively better run producing season. The Yankees scored 968 runs in the American League. So here's the Yankees. I'm going to do the Yankees over here. So they scored 968, where the mean was 793.9, and the standard deviation was 73.5. Okay? Now then I do the Phillies. They scored 892. Well, how does that compare to the Yankees? Did they actually do better than they thought? So the mean of the Phillies was 763, and standard deviation is 58.9. Okay? How many standard deviations away from their mean did they do? So that's the question here. So we're going to use our Z-score formula. Basically, it's x minus the mean divided by the standard deviation. That's the whole idea here. All right, so x is this value right here. 968 minus the mean divided by the standard deviation. I get 2.37. Okay, great. Let's do this for the Phillies. Take x, 892, subtract the mean, and divide it by the standard deviation. Okay, do the subtraction first, and then I get 2.19. So remember, this is how many standard deviations above the mean. Well, the Yankees were 2.3 standard deviations above the mean, while the Phillies were only 2.2. So who had a relatively better season? Well, the Yankees. Had a better season. How do I know? Because 2.37 is greater than 2.19. Okay? That's how I know. So let's look. In 2005, babies born after a gestation period of 32 to 35 weeks had a mean weight of 2,600 grams, it's grams, not pounds, and a standard deviation of 660. In the same year, babies born after a gestation period of 40 weeks had a mean weight of 3,500 grams and a standard deviation of 470. Suppose a 34-week gestation period baby weighs 2,400 grams and a 40-week gestation baby weighs 300 grams. Which baby weighs less relative to the gestation period? All right, so we're going to do the same thing, okay? We're going to do it twice. Let's break down. We have a 34-week baby, and we have a 40-week baby, okay? So let's see. Suppose a 34-week baby gestation period weighs 2,400 grams, and a 40-week baby gestation period weighs 3,300 grams. Okay, which baby weighs less? All right, so now we take it. Here's the mean weight right here. 32 to 34 is the mean right there. So this one gets 2,600. And the standard deviation is 660. So that gives me a Z-score of negative 0.303. So on a 40-week baby, what does it say the average is? So Babies born after gestation of 40 weeks had a mean weight of 3,500 grams and a standard deviation of 470. Okay, and if I subtract that and multiply it, I get negative 0.426. Okay, so which one weighs less relative to the gestation period? Well, think about it. Which one's a smaller number? Well, this one. That's a smaller number. So the 40-week baby weighs less. All right? There you go. Now, more examples of population variance and standard deviation. If you want to watch this, if you don't, that's fine. Feel free to pause the video and try to find the sample variance and population and then see if you get it correct. Okay, that's your choice. You can do that. I'm just doing more examples so you can get comfortable with the process. All right, so the first thing I have to do for population variance and standard deviation is find the mean. This is a sample, so it's going to be X bar. When I add them up and divide by 5, I get a mean of 11. I know that n is equal to 5 and we're dealing with the sample. Okay, so I take my observations, 20, 13, 4, 8, and 10. And I'm going to take that each observation and subtract it from my mean, which was 11. So I get 9, 2, negative 7, negative 3, and negative 1. Then I square it. So I have 81, 4, 49, 9, and 1. Then I add, and I get 144. So my variance is 144 divided by, remember, if it's sample, you divide by n minus 1. So if n is 5, I divide by 4, I'm sorry. So I get 36. So then S is the square root of 36, which is 6. Okay, so there's my variance. There's my standard deviation. All right, one more real quick example, easy numbers to use. Let's find, this one's X bar, so I'm going to use mu as my symbol. I'm going to add them, and I'm going to divide by 5. When I do that, I get a mu of 9, and n is still 5. That's 4, by the way. So observations, 3, 6, 10, 12, 14. I'm going to take that and I'm subtracting mu. Well, mu was 9, so 3 minus 9 is negative 6, 6 minus 9, negative 3, 10 minus 9 is 1, 12 minus 9 is 3, 14 minus 9 is 5. Then I take x minus mu and I square it. 36, 9, 1, 9, 25. Add them up, and I get 80. That's the hard part. Now, so variance is sigma squared, so I have to take 80, divide by 5 observations. That gives me a variance of 16. And for standard deviation, I'm going to take the square root of 16, and I get 4. So, by the way, variance is always going to be units squared, and standard deviation is just whatever the unit is, feet, inches, whatever. Okay, variance is units squared, which should make sense because it is squared. All right. Now I know that's a lot of information and a lot of calculations, and we'll go through this in class as well. But hang in there, and we'll get you through it.